Okay, so today we're going to start taking a look at connecting the graphs of, or connecting f prime and f double prime with the graph of f. So what does the first derivative, what does the second derivative tell us about our graph of f? That's what we're going to be shooting for here. And today we're going to look at this thing called the first derivative test, which we can use to find local extrema. And you guys are actually kind of sort of using that already a little bit. And we'll just kind of like lay down the rules a little bit more succinctly today. We'll talk a little bit about this thing called concavity. And as a result of that, we'll talk about what it actually means to be a point of inflection. We kind of hinted at that earlier today. And then there's this thing called the second derivative test, which also allows us to help find extrema. And then once we've got all that stuff pulled together, then we can actually start to sketch graphs of f, f prime, and f double prime given some other one. Okay, so if we know like what's the graph of the derivative, we can try and work backwards and get a sense of what the original graph looked like. Or if we have an original graph, we can try to sketch the first derivative or even the second derivative, that sort of thing. So that's kind of where we're going with it, but we need to lay down some of the groundwork here with this first derivative test to begin with. Okay, so there are a couple different parts to this. So if we know we have a critical point, C, of a continuous function, then the following is true. So, number one, if f prime changes sign from positive to negative, at C, then C is a what? You guys could probably answer this for me right now, based on what we've studied so far. If the derivative changes from positive to negative, it's a maximum, right? Because the derivative, remember, measures slope. Okay, and if the derivative is positive, it's increasing. If the derivative is negative, it's decreasing. So if that changes sign from positive to negative, then C has got to be a maximum. Now, if we're talking about a continuous function, there are two different ways this could happen. Okay, it might be differentiable at C, or it might not. Okay, so it could look like this, and here's C. Okay, so it could be a situation where it's a nice, smooth, differentiable curve there, and derivative is positive, derivative is negative, okay, maximum. But the case that people don't usually think about is, well, this could still work if it isn't differentiable there. The mean value theorem doesn't work if it's not differentiable, but the first derivative test still works. So if you had something where, okay, here's C, maybe it comes up like this, and then comes back down like that. Okay, so take a look. For the first derivative test to work, it has to be a continuous function. Is this graph right here continuous? Yeah. It says if f prime changes sign from positive to negative, it's a maximum. Is f prime changing from positive to negative? Yes, it is. Now, what's the value of f prime right at c on this one? Doesn't exist, right? Because it's a cusp. But it still changes sign from positive to negative at that point, so it could still be a maximum. Okay? So both of these two situations are in play for using the first derivative test to identify where you've got a maximum. Okay? Now before, we were kind of searching for them by, okay, take the derivative, set it equal to 0, because that's where you might have a max or a min. But that's kind of only part of the story, because you could have these non-differentiable places too, right, where it could happen. So that's what it would look like then if you had that situation. Okay, so next thing, I guess you guys probably see this one coming. So if f prime changes sign from negative to positive, then what do we know about C? It's a minimum, right? And I'll draw you some fun pictures for this one too. I know you would be. Anyway, okay, so first one, again, f prime starts out negative, it's decreasing, and then it switches to increasing there, so that one works. And then, again, it could be non-differentiable. So maybe you've got a situation that is something like that. All right, again, in either case, the first derivative test works. We know there's a minimum because the derivative has changed from negative to positive. Okay. Number 3, this is a situation we ran into with that one problem where I said it was a point of inflection. So if there is no change in f prime, then we don't have any extreme value. Okay, now sometimes this ends up being a point of inflection. Sometimes if it's non-differentiable, it's not, so it's kind of a little bit sticky there. We'll talk more about those points of inflection later, though, so it'll help clear it up. But I'll just show you. The situation in this first box is, okay, let's say there's no change in f prime, but C, remember, still has to be a critical point. And to be a critical point, the derivative still has to be 0. Okay, so it would be something like where you've got the function coming along, it's increasing, it levels off, and then it increases again, kind of like that. So C, the derivative is 0 at that point. There's a horizontal tangent there. But the value of f prime around C hasn't changed. It's positive, 0, positive again. So no extreme value there. It can't be a max or a min. And this could also happen if you have a non-differentiable point again. So if it looks something maybe, let's see, we're the one that we were talking about today? Yeah? It was like the first one. Yeah. Yep. It was called a point of inflection. So that first one, that's a point of inflection. This second one is not a point of inflection. Okay? But, again, if we're just talking first derivative test, the only thing that we're using here is the fact that if there is no change in f prime on either side of c, then there's no extreme value. So notice in the second one there, it's not differentiable at c, but the derivative is negative, then there's the point c, and then the derivative is negative again. No change, it's not a max or a min. Okay, that's the important thing. All right, and then at endpoints, this is the last little piece of the puzzle here. So let's say the left endpoint of an interval so if we have f prime of x is less than 0 after a, then we've got, let's see, that would be next. So that's going to be a max. And if f prime of x is greater than 0 after a, then we've got a min. Okay, so I'll kind of show you what I'm talking about here. So we're talking about a left endpoint here, right? So the edge of an interval, we're starting at like a. And so if the derivative is negative after the endpoint, it means it starts to decrease after that endpoint, right? So it would be doing something like this. Okay? Do you see how that point has to be a maximum then? Right? And then similarly, if the derivative is positive after that initial endpoint, so it starts going up, then a has to be a minimum. Okay? And the right endpoint does kind of the same thing. Okay? It's just on the other side. And I'm not going to draw pictures for these because I think you guys get the gist now. But if the derivative is less than 0 before this point b, which would be at the end of the interval, okay, so derivative is negative, coming down to an endpoint, what's b? Is it a max or a min? Has to be a min. And then the other, if f prime of x is positive, greater than 0 before you get to b. Okay, so it's increasing as it gets to b, then b has to be a max. Yeah. Bless you. Okay, so that's the first derivative test. Okay, covering all our bases there with that. So, how do we use that to help us come up with some information about a function then? So if we know the equation of a particular function and we can get its derivative, then we need to check and see where does the derivative change values from positive to negative or negative to positive, because those are going to be the places where we have maxes and mins. That's what we're going to be looking for. Okay, so let's try that real quick here. All right, so let's take this function, x squared minus 3 times e to the x. So, what do you think is our first step here then? How are we going to start to use the first derivative test? Find the derivative. That's always, yeah. It's in case, yeah. When in doubt, say, take the derivative. Yes, good. Chapter 4, that's what it's all about. We're doing applications of derivatives, so that's a good guess. All right, so f prime of x. What am I going to have to use to take this derivative? Product rule, okay. So derivative of the first, 2x, times the second, plus the first, times the derivative of the second. What's the derivative of e to the x? E to the x. So there's your derivative. And we need to figure out where this derivative changes sign from positive to negative. Okay? And there are two ways that can happen. Where the derivative is equal to 0, it could switch there. And also it could switch places where the derivative is undefined. Okay? So let's talk about this undefined part first. Look at the equation of that derivative. Is there any place that could be undefined? No. Right? There's only 3 ways you can make a function undefined, and that's dividing by 0, taking a square root of a negative number, or doing a log of 0 or negative. Kind of like when you're doing domains back in pre-calc for the first time, we talked about those little rules. Same thing applies here. It's the only way you can have something be non-differentiable if you have its equation. So we don't need to worry about any of that. Okay? So really, we're just focusing on where is this thing equal to 0, because those are potential places where it could change sign. Doesn't mean it will, just means it could. So we still got to figure out where those are at, though. Okay? So 2x e to the x plus x squared minus 3 e to the x equals 0. So any ideas what I could do there to start solving that thing? I think you guys both, you're starting to say take a, I think you were right. Right, yeah, you're going to factor out the e to the x. So e to the x times 2x plus x squared minus 3 equals 0. And then we can use our zero product property and take each one of those products. I'm just going to rearrange this one. Set them each equal to 0 and solve them individually and see if we get anything from that. All right, so e to the x equals 0. What do we got there? How would you solve e to the x equals 0? No, because e to the 0 would be 1. How do you undo an e? Natural log. So you take the natural log of 0? No. So there's no solution to that part. Can't do it. What about the other one? Yeah, we'll factor that. Just looking for, factor. Okay, so x minus 3 and x plus 1. Is that what you said?
Plus 3 minus.
There you go. Okay, good. Just making sure you hit that the right way. Okay, so x plus 3, x minus 1. So our solutions are negative 3 and positive 1. So we need to check. Does the value of the derivative change in between, or on either side of negative 3 or 1? And if so, which way? So do we have a max or a min? So do you guys remember in pre-calc when we made our sign charts? Where we put the zeros on the sign chart and then we had to test to see where was it positive or negative in between, and then we did a little bit of that the other day, I thought. But yeah. Okay, we're going to do that again. Okay? Okay. So, remember, we're not going back to the original function. We're talking derivative here, right? does the derivative change its sign at these places? Okay. So we got to plug some of these numbers in, and remember, we're only concerned with, does it come out positive or negative? Okay. E to the here's an easy thing to remember with this particular one anyway. E to the x. Think about the graph of e to the x. It's always what? Positive, no matter what. So no matter what, it's always positive. So when we do our little sign chart, that's always going to be a plus part of it. Okay. Okay. So something less than -3 into 2x, positive or negative? Negative. E to the x, positive, plus a number less than -3 into x squared minus 3. That would be positive. And then e to the x, positive. So if I do a negative times a positive plus a positive times a positive, what's going to be the result? Well, it could go either way, right? So we have to kind of check, maybe not using that form of it then. Yeah, okay, so let's do this instead. I was thinking that might not work. This right here, take a look. We got, when this is all factored out, we've essentially got that, right? So let's do that instead. Okay, so, because then we got 3 things just multiplied together, and that's going to give us a definitive answer now. So something less than -3, e to the x, always positive. X plus 3 would come out negative. X minus 1, negative. Positive times a negative times a negative. Positive. Okay, so that's definitely a positive interval. Let's pick something between -3 and 1. What might make a good choice? 0, thank you. Okay. So, positive for e to the x. What about x plus 3?
Yeah.
Positive. And x minus 1? Negative. Is not an answer. So what's this one? Negative. And then if I plug in something bigger than 1, I've got positive, positive, and positive. So that interval over there is going to be positive. Okay, so where are our extreme values, and are they minimums or maximums? So at -3. Does the sign of the derivative change at -3? Yes. What do we got? A maximum. So we got a max at x equals -3. What about here? Minimum. Yep. All right. So there you go. All right, and believe it or not, we are out of time. So we're going to hit up all the rest of that stuff on Monday. Okay? Or not. Oh, okay. I think we're okay now. So the first thing we're going to talk about today, with all this graphing stuff and how it relates to the first and second derivative, is concavity. And concavity is a measure of how a function, how the curvature is shaped with a function. So I'm going to give you a few examples here of how concavity looks. So something like this, that kind of curvature is concave down. And concave down can happen like with this one, like when a function is decreasing. But a function can also be concave down when a function is increasing. Oops. So it would look something like that. That's also concave down. Do you guys see how those two are related? Think of it like if the curvature were kind of like rotating around a point, okay? If you could kind of find like the center of the arc, okay? So with this one, it would be like somewhere down over here maybe. And see how this is kind of coming around and that center of that curvature is like below it. Same thing over here. If it's kind of curving around this way, it's still like the center of that curvature would be like somewhere down over here. So it's concave down, it's opening down. And then concave up could be increasing or decreasing, same kind of thing. So if we were, let's see, doing a concave up, could look like this. That's concave up. And then if it were decreasing but concave up, it would look something like this. And you see with both of those, if I had kind of that center of the curvature or whatever, it would be above where the curvature happens. Is that, you guys aren't really saying anything, so is that explanation helpful? Yeah. Do you see that, the difference between the two? Okay. So this gives us a little bit more information about a graph. And the way that we can measure concavity, or the way that we can find it from our equation, is using the second derivative. The first derivative tells us if a function increases or decreases. We talked about that last week. The second derivative, if it's positive, is concave up. And if the second derivative is negative, it's concave down. Okay? So that's an important little connection here. So if f double prime of x is greater than 0 on some interval ab, then f of x is concave up on that interval ab. And then the opposite is true too. If the second derivative is less than 0 on an interval, then it's concave down on that interval. All right, so as long as we can calculate what the second derivative is, and then use a sign chart kind of like we did last Friday with the first derivative, we can figure out where a function is concave up and where it is concave down. Okay, so that's going to be kind of our next thing that we're going to want to test for here with some functions. So let's try this once. So let's take a look at let's do f of x equals 3 plus sine x, and let's put it on the interval 0 to 2 pi. Not including 0, not including 2 pi. And let's try to figure out where is f of x concave up and down. All right, so where should I begin?
The derivative.
Yeah, good answer. The derivative. Okay, so what is the derivative of 3 plus sine x? Cosine x. All right, got the first derivative. What should I do next? Second derivative. Good answer. You're welcome. All right, so what is the derivative of cosine? Negative sine. All right, so now we need to do a sine chart, no pun intended, because it's the sine. We're doing a sine. Yeah, okay. We need to do a sine chart, figure out where is negative sine x, positive and negative. First things first, though, we need to figure out where is sine equal to 0. Or where is, I'm sorry, well, I guess technically, where is negative sine equal to 0? What values of x? Because that's going to set up where we break apart our sine chart here. So think unit circle. Wherever sine is 0, negative sine would be 0. So where on the unit circle does that happen? 0, pi, and 2 pi. Now, technically, 0 and 2 pi are outside the range of our domain that we started with, but it doesn't matter. That's still, we can start and end there. That's fine. Okay, and so then let's just test some points in between. So in between 0 and pi, negative sine, what do we got? They try maybe like pi over 2. So what is negative sine of pi over 2? Negative 1. Okay, so this interval is negative. All right, and then test a point between pi and 2 pi into the original function. Not the original function, I'm sorry, into the second derivative. And what do we get there? Is it positive or negative? Positive, yeah. If you did like a 3 pi over 2, that'd probably be a good choice there. But this comes out positive. Okay, so that means that this particular function f of x, the original function, is concave up over what interval? Nope. Concave up. Pi to 2 pi, right. Concave up, second derivative is positive. So pi to 2 pi, and then f of x is concave down. That one's the 0 to pi. All right, so let's take a look at 3 plus sine x. See if we can, on our calculators, like visually inspect this thing and check for concavity. See if it matches what we came up with, what it should be here. All right, so make sure, number one, your calculator's in radians. Make sure the window is an appropriate size where you can see everything. Okay, remember, we're only going 0 to 2 pi. And check it out. See if the concavity matches the way you think it should there. All right, so when you're looking at the graph, remember, we just said we believe the graph of f of x should be concave up between pi and 2 pi, and the graph of f of x should be concave down between 0 and pi. Is that what we're seeing on the graph there? Yep. Here's what I got. All right, my scale that I chose to use at the bottom there, I was going every pi over 2. Okay, so right in the middle, that's pi. Okay, so concave down, concave up. Okay, got it. Now this point right in the middle where the concavity changes, so in this case it was at pi, that has a special name too. And that's called a point of inflection, okay, which is the next thing we're going to talk about. So a point of inflection, simply stated, is a point where the concavity changes from one to the other. Okay, so let's jot that down because that's kind of important. All right, and it could go either way. So either concavity goes from positive to negative, or it goes from concave up to down or down to up. It doesn't matter either way. Okay, now, usually, it's not always the case, but usually, what's true of the second derivative at a point of inflection? What did we find in the last example? Think about where the point of inflection was. What was true of the second derivative at that point? Let's go back to that one really quick. Where's the point of inflection on this example that we just did? At pi. What was true of the second derivative at pi? Equals 0. Okay? Like 99% of the time, that's going to be the case. All right? So I'm just going to put that down here. It's not technically part of the definition because it's not always true, but usually it's pretty safe. Okay, now why am I saying usually? So what else could happen? Well, point of non-differentiability, you can have a change in concavity over those two. There's a corner, cusp, something like that. Your concavity could change suddenly at those points too. So it's not always simply where the second derivative equals 0. Usually that's the case, but there are those non-differentiable points too that show up that could also happen. Okay, so if you're searching for a point of inflection, you need to consider where is the second derivative equal to 0, but also where is the second derivative undefined, because it could flip over that as well. Okay, but don't usually see that. It's usually just check where it's 0 and go around it. So today it's just where the concavity changes. So if you have your sign chart set up, you can do that, and you're safe. So okay, so we get done with the point of inflection. Test. So what I want to get to next. This is going to become, I think, at least it did for me, it's going to become your new best friend when you're searching for maximums and minimums, is this second derivative test. A quick sketch of a graph here that has a maximum and a minimum. We're going to discuss the second derivative with this graph here for just a minute. Okay, so let's say we got that. Here's a max. Here's a min. And your point of inflection is probably somewhere about right there. So we'll just call it poi, point of inflection. Okay, so what's true? Let's look at just the maximum to start with here. What's true of the first derivative at the maximum? Mm-hmm. What's true of the second derivative at that maximum? Remember, second derivative measures concavity. What's the concavity at that maximum? Is it up or down? Second derivative would be negative, right? Because it's concave down. Okay? So at that max, first derivative equal to 0, second derivative less than 0. Every time you have a maximum, unless it's a point of non-differentiability, as long as it is continuous and smooth, differentiable, all that stuff, that's true of a maximum under those conditions. Nice smooth curve. A max is going to have a first derivative that is 0, because it's a horizontal tangent, and second derivative less than 0, because it has to be concave down to be a maximum. Does that make sense? Okay. Minimum, same kind of story. Okay, first derivative has to be what? 0. And what about the second derivative down here? Greater than 0. Okay, that's the second derivative test. Okay. Oh, and our OI here, second derivative equal to 0. First derivative could be whatever at a point of inflection, we don't know. But second derivative is 0. Okay, so your second derivative test, mainly focusing on just these two things, though. Okay, if it's a continuous differentiable curve, maximums have a derivative that is negative. Minimums have a second derivative that is positive. And I know that's a little bit backwards in your head, but you got to think concavity, right? Concave down produces maximums. Concave up produces minimums. So you got to keep it that way. So let's just write this down. So a local max will have the first derivative equal to 0, second derivative less than 0, local min. First derivative equal to 0, second derivative greater than 0. And all of this is contingent on the fact that you have a continuous differentiable function. As soon as you have, like, you know, corners, cusps, tangents, that kind of thing showing up, points, then this stuff kind of goes out the window. But nice smooth curves, you can do this, and it works. Okay, so let's try it. All right, let's say we got x to the third minus 12x minus 5. What are the first two things that you should do? First and second derivatives, yes. If I'm going to use the second derivative test, I do both. So start with that. First derivative, 3x squared minus 12. Second derivative, 6x. Okay. Oh, and I should probably put this thing on an interval. Nah, I guess we don't need to. We're just looking for extrema. So, okay. So I don't know. I want to know where do we have maxes and mins on this one? Okay. So we're going to start the same way you did before. What did you do to find maxes and mins? No, we don't need a sign chart. Because what has to be true about the first derivative for maxes and mins? Equals 0, right? So that's where we started before. We didn't necessarily jump into the sign chart, but we just took a look at the first derivative and where's that equal to 0, right? So let's pull that out and do that. So 3x squared minus 12 equal to 0. These are going to be places that we can have maxes and mins. So if we solve that, 3x squared equals 12, x squared equals 4, so x equals plus or minus 2. And then the question always was, well, how do we know if it's a maximum or a minimum? And then we had these other techniques of, then we could make a sign chart and check and see where is it increasing or decreasing around those points and do that. But with the second derivative test, we don't have to mess with that. Because we know with the second derivative what should be happening if we have a max or a min, right? So we have our 2 points, 2 and negative 2. It's just a matter of at 2 and at negative 2, is the concavity up or down? How can we test that really quick? Yeah, plug those into the second derivative, right? So into 6x, let's see what we get each time. So f double prime, say pi 2 is 12, and f double prime of negative 2, we get negative 12. Now the number itself doesn't really matter. What are we really just checking for? Positive or negative. Okay. So at x equals 2, is it a max or a min? Min. Remember, it's better than what you think. If it comes out positive, it's actually a min, and then this is going to be a maximum. Okay. So x equals 2 is a local min, and x equals negative 2 is a local max. There's where your extrema are. And if you wanted to have ordered pairs for those, if the question asked for that, what would you do with the 2 and the negative 2? Exactly. I want to know what's the y that goes with this x on my original graph, right? So plug it into the original one, and then that way if that's what they're asking for. Okay. So take a minute. Let's put this one in the calculator real quick. See if we did good work here. We're thinking x equals 2 should be a min, x equals negative 2 should be a max. Graph that function, see if that's the case. It should work. I hope it works. Going to want to probably change your window too from the last one. All right, so at equals 2, are we seeing a maximum? Are we seeing a minimum? Does silence still mean yes? Okay. Does x equal negative 2, does that look like a max? Should be. Getting something kind of sort of like that. So, yeah, that makes sense. We got a maximum when x is negative 2, minimum when x is positive 2. So, kind of the idea is using the second derivative test. Step in the process here that we're going to do with all of this is we're going to take these ideas about concavity and where is it increasing and decreasing and where are there points of inflection and maxes and mins and all of that. Since we're able to find all of those things, all I need is an equation of a function, and I can sketch a pretty accurate graph of it. So I have all this information I can come up with using the first and second derivatives. So that's going to be kind of our final stage here is, can we take all this stuff and put it all together and make something of it? Okay, so let's take a look. All right, so let's just see if we can sketch a graph of x to the fourth minus 4x to the third plus 2. Doing all this stuff. All right, so first two things I'm going to do? Let's get our two derivatives down so we can go back to those and use them as needed. So this is 4x to the third minus 12x squared. And our second derivative, x squared minus 24x. All right, so let's start with some maxes and mins. Let's do that. So to determine if we've got local maxes, local mins, use our second derivative test to do that. Okay? What we need to do in this process is what? Yeah, okay. Want to take the first derivative, set it equal to 0. So we've got 4x to the third minus 12x squared. Okay, so how would I go about solving that? Okay, take out a 4x squared. Okay, so what if I got as solutions then? So I got 0 and 3, yeah. Okay, and what do I do with 0 and 3 now then? Right, take them in that second derivative and check to see what am I getting for the concavity, right? Okay, so double prime of 0, what is that? 0. So what the heck's going on there? Point of inflection. We've actually found a point of inflection there, right? So first derivative equal to 0 does not always give you simply a max or a min. Could be a point of inflection. In this case, it is. So there's our poi. And the other one, if we plug in an f, do f double prime of 3. Maybe you need a calculator to quick verify it, but 36? Okay. So what do we have at 3? That's got to be a min. So we inadvertently found an inflection minimum. Now, does that mean that's the only point of inflection this graph has? Could have more than one, right? So we can still check that out, okay? So we'll go for other points of inflection here. So how would I search for other points of inflection? Right. So this is going to be where the second derivative is equal to 0. So 12x squared minus 24x equals 0. Okay. How would I solve that? Okay. Yep. Take 12x out. So x minus 2 would be left. So any other points of inflection other than 0? X equals 2. Mm-hmm. So we have 2 points of inflection on this graph, at 0 and at 2. And apparently we have just one minimum at 3. And that's it. Okay? So, Let's check for some concavity then. Where is this thing concave up? Where is it concave down? How do I do that? Which of the two derivatives am I going to be working with on this one? First or second? Nope. Second. Yeah. We talked. This is the first thing we talked about today. Concavity. It's concave up when the second derivative is positive. It's concave down when the second derivative is negative, right? Well, what did we actually do with the second derivative? Flip back in your notes if you need to. How did we check for concavity? What did we make? Sign chart. Okay, so we need to do a sign chart here. And we start with these two places that we know are points of inflection already, 0 and 2, right? And we're going to test in and around those points to see what else we have. So, right, exactly. That's a min. That's not a point of inflection. So, now I plugged in a 3, and the second derivative came out positive, right? So we know this is positive over there. What's a number between 0 and 2 that I could plug in? 1. Okay, so plug in a 1 into the second derivative. What do we get? Is it positive or negative? Comes out negative, yeah. And then if I plug in a negative number, that should come out positive then, right? So that would be negative times a negative. Yeah, so that's going to be positive. Okay, so we got some intervals for concave up, concave down, right? So concave up is going to be negative infinity to 0, also 2 to infinity. Concave down is going to be 0 to 2. All right, so we've got a minimum, 2 points of inflection. We know where it's concave up and down. What are some other things that we can find that we haven't done yet? That might be helpful. We did it like middle of last week. I'll help you out. Increasing and decreasing. Kind of running out of room here. Hopefully you have more room than I do. Okay, so increasing and decreasing intervals. How for that? What derivative are we working with if we're talking about increasing and decreasing? First derivative. And just like concavity needed a sign chart for when is it concave up or down, increasing and decreasing intervals, we have to do a sign chart again, but for the first derivative. Okay, so let's check that out. Now, where are the two places where the first derivative is 0? 0 and 3. So, guess what? Here we go. 0, 3. So we got to test around those. Okay, so let's see. Less than 0 in the first derivative. It might be more helpful to use this right here when it's already factored. That's usually the easier way to go. If I plug a negative into that, what's the result going to be? Negative. We're going to have a negative number squared, which is positive, and then a negative number minus 3. Ultimately, that's going to come out negative. Neat number between 0 and 3 you can plug in. What happens there? It's also going to be negative. So you get a positive times a negative, so that's also negative. And then, what about a number bigger than 3? That's positive. All right. Now, when you're listing these intervals, we've got negative infinity to 0, 0 to 3. First derivative comes out 0, x equals 0. Okay, so it's not technically increasing through 0. It kind of stops at one point and then keeps going. So I apologize because I'm running out of room. But increasing is only the interval 3 to infinity. Decreasing, negative infinity to 0, 0 to 3. That's really small, but information we're going to use to help make this graph then. We've got this, we've got this, we've got that, we've got that. Yeah.
What kind of graph would it happen where it was like what happened after that?
We're at 0?
Yeah.
Okay. So what happens is you have a derivative equal to 0. All right? So it levels off. So it's increasing, right? Or no, it's decreasing, right? It's decreasing. So it's coming down. Then when it gets to 0, it levels off. But then after 0, it's supposed to decrease again, right? So then it comes back down. Decrease, level off, decrease thing.
Okay, so it'd be kind of like
Yeah.
it's all going up, but it has a flat.
Right. Yeah, exactly. Yep. What I would like you guys to do, another thing that's helpful with the original graph, I don't know if you guys thought about this at all, but equals 2, if you look from the original graph here, this is another piece of information you can use. What is this? What's this 2? What is it? I think I heard you say it. The y-intercept. So you got that to work with too. Okay? So, page or on the same page, wherever you have some room, you try to sketch this now best you can. Knowing what you know about points of inflection, maxes, mins, all that kind of stuff. See if you can sketch it out by hand. Best you can. This is a skill we're going to continue to kind of refine as we move along. But I want you guys to just kind of try it on your own for a minute. And then I'll show you what this graph looks like after you guys are done. And see how close you came. It's going to take a little bit of trial, erase, fix it, erase something else, fix it, probably a little bit. So you got your point of inflection right there. It's at 2, right?
Oh.
Yeah. Now, the one thing we didn't do with this, that we really didn't have the capacity to do, was to figure out where the x-intercepts were. So we might have some variation there, a little bit of where your x-intercepts are placed versus mine. But the y-intercept is locked in. The way the curvature of this thing works is kind of locked in with the concavity and all of that. So that's kind of what we're going to be checking against here. So try to kind of ignore x-intercepts for the moment. But I'll let you guys finish up here. Looks like a few that are still finishing up. All right, I'm going to unfreeze it. Are we ready? Silence means yes. Okay. See how you did. Oh, fuzz. Anyway, you can kind of see it. You can see it anyway, though, about where things should be. Let me fix this. I love this thing. As soon as you... Whoops. That's better. Okay. So, here's what's happening. From negative infinity to 0, it's decreasing, correct? So it's coming down, inflection at 0. Okay, so concavity is going from concave to concave down. Do you guys see that? Cavity changes there. First derivative is supposed to be 0 there, so that's why it levels off. And then it's supposed to decrease again, so it starts to decrease again after that. When you get to 2, inflection, okay? Still decreasing though, right? So it's still decreasing, but the inflection changes, or the concavity rather, changes. And then when you get to 3, we said it had to be a minimum. And then it's going to come back up and increase after 3. Okay? So, how'd we do with that? You guys get pretty close? I saw a few out there that looked pretty darn good. So, oh, lovely. So, I'm going to let you guys get started on your homework while we have a little bit of time here. I would, however, want you to pay close attention to one particular example in your reading. Okay? Remember, you still got to read through the section. Example 9 says analyzing a discontinuous derivative. All right, make sure you read that one a little closer than the rest. But what?
I got it now, guys.
Okay.